Okay, think about this for a second. Have you ever wondered what actually happens when you type a simple math problem like 5 plus 5 into your calculator or computer? I mean, it feels completely instantaneous to us, right? But there is this invisible, massive translation gap happening right under your fingertips. You see, the hardware inside your device literally cannot understand the number 5. It doesn't know what a plus sign is. It doesn't speak any human language at all. It only understands one thing: microscopic electrical signals that are either turned on or turned off, ones and zeros. So welcome to this explainer. Today, we're going to bridge that translation gap and uncover the secret language of your computer.
Here's a quick look at our agenda. We'll start with the language of computers, then move on to grouping bits from bytes to words. After that, we'll cover converting decimal to binary, translating binary back to decimal, unpacking MSB, LSB, and negatives, and finally, octal and hexadecimal systems. Let's dive in. Section 1. The language of computers. Right off the bat, there's a huge contrast between our world and the machine world. In the human world, we use the decimal system. It's a base 10 system, meaning we rely on 10 distinct digits, 0 through 9, to communicate values. And this makes perfect sense for us. We have 10 fingers, so counting in tens is incredibly intuitive. But over in the computer world, machines operate entirely on binary logic. That's a base 2 system. They only get 2 digits to work with, 0 and 1.
So binary logic is absolutely crucial. It is the foundational system of all computing. Because computer memory and processors are basically made up of billions of microscopic transistors that can only hold a high voltage or a low voltage, they simply can't process decimal numbers directly. There's just no physical way. This base 2 binary system is the mandatory bridge for absolutely all digital data.
Section 2. Grouping bits. Bytes to words.
It all starts right here. A bit, which, by the way, is just short for binary digit, is the absolute microscopic foundation of computer storage. It's just a single state, 0 or 1. Now, alone, a single bit doesn't really do much, but it's the core building block for the whole shebang. When we group 4 of these bits together, we get what computer scientists playfully call a nibble. I love that term. A nibble is really useful because it's the exact size you need to represent single decimal numbers in binary code, or single hexadecimal numbers, which we're going to look at a bit later. And from there, memory scales up exponentially, kind of like a giant puzzle. 2 nibbles make a byte, which gives us 8 bits. Group 2 bytes and you get a word, representing 16 bits. And 2 words make a double word, which is 32 bits. So when you hear people talk about a 32-bit operating system, this is exactly the size of the data chunks it's processing at any given moment. Pretty cool, right? Section 3. Converting decimal to binary. Okay, so if you want to feed a computer the number 50, you've got to do a little math first. We use what's called the repeated division method. Let's use 50 as our mental test case. We divide it by our target base, which is 2. So 50 divided by 2 is 25, and the remainder is 0. We write down that 0. Next, we divide 25 by 2. That gives us 12 with a remainder of 1. We record the 1. We just keep repeating this process on the quotient until we finally hit 0. Then, the magic step, to get our answer, we read that column of remainders from the bottom all the way to the top. I'll give you a second. Any guesses on what the final output for 50 looks like? Did you guess it? The final binary result for the number 50 is 110010. Whenever you type the number 50 on your keyboard, this exact string of ones and zeros is literally what races through your computer's logic gates. No way around it.
Section 4. Translating binary to decimal.
Now, you might be wondering, how do we reverse this process? How do we translate that machine code back into human numbers? Well, we use something called positional weights. Think about our normal decimal system. You have the ones place, the tens place, the hundreds place. Binary works exactly the same way, but instead of multiplying by 10 every time you move left, it multiplies by 2. Each binary position carries a physical weight that doubles as you move to the left. So the far right is 2 to the power of 0, which is 1. Move left, the next spot is 2, then 4, then 8, 16, 32, and so on. To convert from binary back to decimal, you just look at where the ones are sitting and add up those weights. Actually, if you want a shortcut and don't want to use that long division method to write binary, check out this subtraction trick. Say we want to convert 25. We just find the largest positional weight that fits into 25, which is 16. Boom, put a 1 in the 16 column. We have 9 left over. The next largest weight that fits is 8. Put a 1 in the 8 column. We have 1 left over. Put a 1 in the 1 column.
All the other columns just get a 0. So the result is 11001. And here's an absolute game changer of a fact to help you check your work. Odd numbers, like 25, will always have a 1 at the very end. Why? Because literally every single other positional weight is an even number. The only possible way to make a binary number odd is to activate that one column on the far right. Section 5. MSB, LSB, and negatives. So not all bits are created equal. The most significant bit, or MSB, is the bit sitting all the way on the left side of your number. Because it holds the highest positional weight, it carries the most mathematical impact. On the flip side, the least significant bit, the LSB, is all the way on the right, and it usually just carries a tiny weight of 1. To see why this distinction is so important, imagine the binary number 10101. That's decimal 21. If a tiny error happens in the computer memory and the least significant bit on the right gets flipped from a 1 to a 0, the number just drops slightly. It goes from 21 down to 20. It's a small error, but if a memory glitch flips the most significant bit all the way on the left from a 1 to a 0, the value crashes all the way down from 21 to 5. This perfectly illustrates why the MSB is absolutely critical for data integrity. But the most significant bit actually has another, arguably more important job. Which brings us to a huge question. How do computers store negative numbers if they only understand ones and zeros? There's no physical minus sign in the hardware, right? The answer is a brilliant workaround called 2's complement, which basically turns the most significant bit into a sign indicator. If the MSB is 0, the number is positive. If it's 1, it's negative. Let's methodically walk through this, converting a positive 10 into a negative 10. Step 1, positive 10 is 1010. Step 2, we add a 0 to the front just to show it's currently positive, making it 01010. Step 3, we create the 1's complement by flipping every single bit, so it becomes 10101. And step 4, we just add 1 to that result. Our final binary sequence for negative 10 becomes 10110. Notice how that leftmost bit is now a 1? That tells the computer's processor, hey, treat this as a negative value. Section 6. Octal and hexadecimal systems. Let's be real, typing out 32 ones and zeros is completely exhausting and it's super prone to errors. So computer scientists use higher base systems as a shorthand. Comparing these systems shows why they're a lifesaver. We know decimal is base 10 and binary is base 2, but we also have octal, which is base 8, using digits 0 through 7, and then there's hexadecimal, a massive base 16 system. The base number simply tells you the total number of distinct digits that system uses before it has to add a whole new column. But wait a second. Our human number system only has distinct digits from 0 to 9. So how on earth does a base 16 system work? Well, hexadecimal relies on a unique alphanumeric system. Once you count past 9, you just start using letters. 10 is A, 11 is B, all the way up to 15, which is represented by the letter F. So, the next time you see an F in a hexadecimal color code on a website, you now know it mathematically represents a 15. And the reason octal and hex are so beloved by programmers is that they map absolutely perfectly onto binary. You don't have to do any long division to convert them. Because 8 is 2 to the power of 3, you can convert binary directly to octal just by grouping the binary code into 3-bit chunks using a 4-2-1 weight formula. And because 16 is 2 to the power of 4, you can convert binary into hexadecimal seamlessly by grouping the bits into 4-bit chunks. Yep, our old friend, the nibble, using an 8-4-2-1 weight formula. It's a shortcut that makes reading machine code incredibly fast and efficient. We've covered a ton of ground today, all the way from the absolute smallest bit to complex base 16 conversions. But I want to leave you with this final thought. Take a look at the device you're watching this on right now. If every vibrant color, every single text character, every complex animation, and every system command running in the background right this second is ultimately just a massive, perfectly orchestrated combination of microscopic ones and zeros, what else is possible with simple binary logic? As artificial intelligence and computing power scale up at lightning speed, it's just incredible to think that the entire foundation remains nothing more than tiny electrical switches turning on and off. Thanks for exploring the machine with me. And stay.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.